Okay, hello everybody. I was asked by the Milestone Institute's Natural Sciences Society to give a talk about the future of chemistry. Of course, I have to start by saying that I am working as a physicist, so obviously this talk is going to have a bias from that side. So I really have to stress that this is just an opinion. And also, I have to start with a disclaimer about predictions in general, which is a quote from Bohr that says that it's difficult to make predictions, especially about the future. So, whatever people say about the future, there is a high probability that it's not going to happen. Just for some examples, I put here some pictures about past predictions, which people made in the 19th century about how the 21st century will look like. And you can see that they had like these flying cars, and they used zeppelin kind of stuff in the ocean. Actually, this picture isn't. It's kind of close to what actually is happening, right? We are using certain social media to communicate. So this picture is kind of nice, right? Close to what's happening. But if you think about like what are the biggest inventions in the 21st century, think about the internet, right? That's not even imagined in these pictures. So with all these things in mind, let's jump into what I believe the future of chemistry is. But so to discuss that, first we need to discuss what chemistry is. So for this, I took the Merriam-Webster um, definition. And so that says that chemistry is a science that deals with composition, structure, and properties of substances and the transformation that they undergo. So how can we deal with all of these things in the definition? Chemistry has been a subject which is very experimental. In the past, we did experiments, we learned something about the matter itself. But then we can also say that when we make some conclusions based on the experiment, we can create a theory from which we can predict something which was not known earlier, which wasn't observed in the past, and make experiments to make sure that that prediction is correct or not. If it's incorrect, then we can, like the science works in a way that if predictions, if nature doesn't do whatever we predicted, then that theory was incorrect, and we stop using that theory. But we can actually move forward a bit and just say that we understand what are the fundamentals of matter from the theoretical point of view, make predictions on that without any previous experimental result, and after we made the predictions, we can make the tests with experiments. So when I say that we should understand the fundamental way how nature works, and we speak about matter, then this fundamental description is called quantum mechanics. If you really want to be if you want to go to the details, then it would actually be quantum field theory. But quantum field theory is less relevant for chemistry. It's super relevant for physics, but we can work on matter without that at the level of chemistry. So let's just discuss some things about what quantum mechanics says about matter. And actually, what we really need to understand in quantum mechanics, which is the centerpiece of this theory, is called the wave function. So if you know the wave function, then we kind of know everything about the material. So what is this wave function, and how can we deal with it? The name suggests, it's a function. We denote it with the Greek letter psi, and it's a complex function, which means that it maps complex numbers to other complex numbers, which is maybe if you don't know what complex numbers are, it's less important for now. You just imagine that it's a function. And so, to the question, what we do with it, we essentially input it into the Schrodinger equation. And you probably have heard of the Schrodinger equation, probably you don't know what it is. So if you just want to imagine what the Schrodinger equation is, and just think about it as as this machine from primary school in which you give some input and there is some rule and then there is an output. So these machines are actually in mathematics called operators. So in the Schrodinger equation, we have an operator which is called Hamiltonian that we denote with an H hat, and then we have this psi. So the psi is the input to this machine, which is denoted with H, and then the output is going to be the same psi, but there is an extra E in front of that. So that extra E is the energy. We denote the energy with that. But then the energy of what? So in chemistry, we are interested in the wave function of the electron cloud, right? The nucleus is less relevant for chemistry. All of the chemical processes essentially happen in the electron shell. So if we can understand the electron shell, we really know a lot about matter. So the E is going to be the energy of given electron orbital. And on this picture, I'm showing all the orbitals, like we have this s orbital, p orbitals, and so on. So these are essentially the wave function of those orbitals. Well, actually, the wave function of the electrons, which creates the orbitals. So you can think about like how can a continuous function describe a particle, right? This is a very old problem. I mean, compared to quantum mechanics, it was one of the first things which entered quantum mechanics, and it's called the particle wave duality. So to actually think about this, it's I think easier to just look at this video. So in this video, what we are doing is that we are making experiments first with some ball kind of structure, and then we have a single slit in which we push through these point particles, and in the screen behind that single slit, you see one line of these particles. If you have two slits, then shooting marbles through those two slits will create two parallel lines. If you repeat the same thing with waves, then from that single slit, you will create this kind of pattern. And then in the screen, you will have one slit, one line, and then this kind of pattern, which is making it less and less intensive as you go aside from the middle. And then when you repeat this experiment with two slits in a pound, then what happens is that at each of the slits you have the same thing that you had the first slit, but then these waves will interact with each other, which we call interference. You can have two ways, either destructive or constructive. So destructive means that the waves meet in a way that they destroy, cancel each other. So that those are the spots where you see black things, and then constructive is when the waves add up so that they are making it more stronger. So those are the white stripes in the screen. So just to recap, when we had two slits in particles, we had two lines in the screen, and when we had same thing with waves, then we had this interference pattern. And so now comes, so all of this was classical, right? And now comes the part where we move into the quantum world. So first they did all this thing with photons, so with light. They shine light on a single slit, and they saw one line in the screen. Then they repeated the same thing with another slit, and the result was somewhat surprising because what they saw was an interference pattern. So if you see an interference pattern, that means that that thing is a wave-like object, and then it has to have an interference with something. So they were thinking that okay, maybe like like one photon is somehow interacting with the other photon, and that creates this interference pattern. But then they repeated the experiment where they used single photons. So when you have a single photon that cannot interact, right? So you would expect to have two lines in the screen, right? Because these are like particles. And that's super surprising is that the outcome is an interference pattern. So how can one particle make an interference pattern? It somehow mean that it splits into like two different structure of itself and interacts with itself. And so, just to make the story even more complicated, if you put some kind of measurement in front of the double slit, then the outcome will be different. So that's what we see in a second. It's almost like that the particle notices that it's being observed, and it decides to act differently. Obviously, it's not really about the observer, it's about the fact that there is some interaction with the system from an outside system. When you did the measurement on it, then the measurement itself made, made the results different. Okay, so going back to the talk, essentially when I said that we have these orbitals, then the electron orbitals are defined that it's the probability of the electron being in that region with a given percentage, 90%, let's say 90% chance that the electrons are in that region. So how do we get probabilities out of the wave function? So what you need to do is that you take the absolute square of the wave function in a given small piece of volume. And so one other notion is figured out by Dirac. This is called the bracket notion. But actually, this is just different notion. Means the same thing. I don't think we need to go into the details for that. But but there is one more thing which we need to discuss with this, is that if this thing, the psi squared dV, is a probability being in some small volume, and then you're adding together all the probabilities of being in some volume up to get the whole universe, then this question is what's the probability that a particle is somewhere in the universe, right? And if it exists, then it must be somewhere. So the probability of finding it somewhere in the universe will be one. So this this equation adds up or integrates to one. Integration is really just a very fancy summation. Okay, so in this double slit experiment, for which we saw the video, we had the state when it went through the left slit, or we had the state when it went through the right slit. And then you can put numbers before that, right? And I just said that I had this state when left slit together with the state when right slit. Then if I don't have any number there, that means that they are there once. So is that correct? Well, I need to use this equation which we discussed earlier. We need to take the square of the coefficients and add them together. And what we get is 1 square plus 1 square is going to be 2, but we just discussed earlier that it should be 1. So something is wrong. Instead of this, we need to have numbers for which the square of the sum is going to be 1. So that's 1 over square root of 2. So the real coefficients are 1 over square root of 2 times the left slit plus 1 over square root of 2 times the right slit. And interestingly, when we say that when we make an observation, when we take a measurement, then it's going to be either the left slit or the right slit. And then you can ask the question of how often does it happen? How often do you get one or the other? And so we discussed that the probability of getting one of them is the square of that thing. So if the coefficients were 1 over square root of 2, then the square of that is going to be 1/2. So it's 50-50 chance of getting one or the other state. And then you can see the famous Schrodinger cat experiment with the same notion. You have 1 over square root of 2, the cat being alive, and plus 1 over square root of 2 of the cat being dead. So in case you haven't heard of the Schrodinger cat experiment, it's about that you have some quantum process, like some particle decaying in a given time period. And so if it does decay, then it will hit some kind of detector, which then hits a hammer, and the hammer hits some poison, and then there is a cat in a box where the poison is, and the poison kills the cat. So the cat being alive is connected to the quantum process of the particle being decayed or not. And since in half of the half time of the particle you have 50% chance of being decayed, that means that the cat is 50% chance of being alive until you open the door and then you see that it's either dead or alive. But until you don't do that, it's in this so-called superposition of these two states. Okay, so what can this superposition be for electrons? So we need something which is like two different states. Like in earlier we had the left or right state. We need something similar. So that is called the spin. The spin is sometimes just denoted that the electron is spinning, and because it has charge, there is a magnetic field created, and if it's spinning to the right, the magnetic field show up. If it's spinning to the left, then the magnetic field will show down. So you have two states, up and down. And then you could say that okay, you have the same superposition of these two states, and the coefficients should be the same, 1 over square root of 2. And then you have a description of the electron. So I said that if you know the wave function, then you will know a lot about it. So in this picture earlier where I showed the orbitals, in the right top corner there was this equation that shows the solution for the Schrodinger equation, so the wave function for hydrogen-like particles. So you see that there are coordinates in this equation, and then there are some other letters, N, L, and M. So these are the so-called quantum numbers, the principal, the angular momentum, and the magnetic quantum number. And essentially, when you give these numbers, you can describe your atom. So you only need to input these numbers into the wave function to get a description of your given atom. So if you want to describe hydrogen, it's enough just to say that it's 1s2, so it means that n equals 1, l equals 0, and then you have two electrons. On it. Like that's actually helium, right? Because I have two electrons, but yeah. So you can ask the question that do we really just have hydrogen in the world? And of course, the answer to that is not. But the solution, the analytical solution to the Schrodinger equation exists only for a few cases, including the hydrogen. For anything else, we need to make approximations. But the point is that when you have these quantum numbers, you can define an element. So if you want to define what the oxygen atom is, then you will say that it's helium plus 2s2 plus 2p4. And the thing is that our goal, our definition for chemistry was to describe materials, substances. And now we are at the point that we know what is the analytical solution to hydrogen. We can, from that, kind of build up oxygen. But essentially, we want to have even bigger stuff, right? It's not only that we have atoms in the world, we have molecules. So for that, there are two competing models, the valence bond theory and the molecular orbital theory, for which I will now just mention the molecular orbital theory. And what it essentially does is that it combines the atomic orbitals into so-called molecular orbitals. You can do this two ways. One of them is called the bonding, and the other is called the antibonding molecular orbital. So in the bonding case, you add the atomic orbitals together, and in the antibonding case, you subtract them from each other. So that might sound weird on the first hearing, but if you think about what the requirement was earlier, we just said that the square of the coefficient should add up to 1. And the square of minus 1 over square root of 2 is the same as the square of the plus 1 over square root of 2, both of them are 1/2. So because of the squaring property, you can add things with negative signs and get the same thing. So just some visualization. If you add an S kind of orbital to PZ kind of orbital, you get something which is called a sigma orbital. From the S, we move to the Greek sigma, and it looks something like this. And then then you add them with a minus sign, and this is what you get. And please note that at the axis it is 0, so the wave function is not continuous in this case. Okay, so let's build some molecule. Let's build the oxygen molecule. We discussed that the oxygen atom is helium plus 2s2 and 2p4. So on the 2s orbital, I put 2 electrons, right? I follow the Pauli rule that the spins have to be different. So when I put there one electron with the up spin, the second one has to be there with the down spin. And then for the 2p orbitals, I have three options, and then I follow the Hund rule, which means that I should put the electrons in a way that they are parallel with the spin. So I put first electron here, and here, and here, and then I have to put the fourth electron that has to go one of the places. So, and then we need to follow the Pauli exclusion principle, and that spin has to be different. So I said that when we are building molecular orbitals, we essentially adding the atomic orbitals. So when we do that, the letters kind of change to Greek. There are some details there, but let's not go into the details there. So from the S you go to a sigma, from a P you go to a pi, and then you do the same thing. We, we add, we build up the electrons. This is also called the Aufbau principle, right? And we are building up elements just by putting the electrons on the minimal energy. So you put things to the sigma, and then sigma here, and then like you follow the same principles, Hund rule and Pauli principle, and then when you reach this point, you want to follow the Hund rule and want to have two parallel things, two parallel spins. So that has some consequences. Like we discussed that you can imagine the spin to be like a tiny magnetic field, and when you have a magnetic field showing up and a magnetic field showing down, those are cancelling each other and you don't have an effective magnetic field. But in this picture, we have two spins showing up. So that means that each of the oxygen molecules have an extra magnetic field. And so that's something new, something which you didn't see in previous theories. And now we can make an experiment. Is oxygen really magnetic? And this video is about that. So they are putting well, okay, first of all they had the liquid nitrogen going through a very strong magnet, and you see that there's nothing really to see there. And so that means that nitrogen is not magnetic material. And how they are doing the same thing with liquid oxygen, and we see that the oxygen stays there. So this is called actually diamagnetic properties, diamagnetism. When there is an extra field, um, then until the oxygen evaporates, it stays there. So that makes us very happy, right? We figured out something just based on theory, and it seems to be true. It seems to be something which nature is doing as well. So that's nice, but still we are at the level of oxygen. What about bigger things more like DNA molecule or some proteins? Can we do that? And unfortunately, we can't. Not yet, at least. Um, if you have big computing farms, you could do some smaller molecules, but you also need to use a lot of approximations. So here comes my bet for the future of chemistry, which is kind of a safe bet actually, if you think about it, and a natural thing to say. That is that why not use the quantum nature itself to simulate substances? So why not go to quantum computers and use the quantum computers to simulate quantum mechanics or quantum chemistry? So for that, I should go into the details of what a quantum computer is. But before that, we need to ask the question of what a computer is. So a computer is a binary machine following algorithm. It is based on a bit, which is short for binary digit, so that can be either 0 or 1. And then a quantum computer has something which is called qubit, quantum bits. And so the main difference between the two is the superposition principle. So when we have a classical bit, that can be either 0 or 1, so that has two states. When you have n bits, that's going to lead to two n states. In a quantum computer, when you have two qubits, that can have four states, which are the up, down, and then the superposition of the up and down with the plus sign, and the superposition of the up and down with the minus sign. So it follows an exponential um, distribution. So when you have n qubits, that leads to 2 to the power of n states. So that's already 1024 for 10 qubits. And it's already more than a million for 20 qubits. Okay, so where do we stand with all this thing today in 2020? And the answer is that there is a huge effort put into quantum computing everywhere in the world, including actually Hungary. There is a quantum computing program in Hungary. Of course, the biggest companies are working on that. As of now, the biggest computer is from Google, which this 53 qubit computer, and IBM is also putting a lot of effort into it. And so, actually, one interesting and exciting news, which was announced like a month ago, maybe 2 months ago, is that Google wants to create a 1 million qubit processor by the end of the decade, so by 2029. So that means that the number of states is 2 to the power of 1 million. So that's something using which we can already simulate matter ourselves. So that's a huge deal for chemistry, and by that it's a huge deal for biology, and of course it's a huge deal for physics too. Um, but I have to actually note that having the hardware, the technology for that is not enough in itself. We need to create new algorithms which can deal with the quantum computing. And actually, one relevant thing for that is that I put here this link that that's about that IBM allows users to join their quantum computing program, and so that means that there are some relatively low qubit number computers which you can use wherever you are in the world. And it has also tutorials, and those one of those is actually quantum chemistry. So you could find that, and you could have fun with it. You could create your own algorithm and just work use a quantum computer by yourself. So that's my bet on the future of chemistry. As I said, it's kind of a safe bet, but I really wanted to show you what quantum chemistry is as of now and what it could be in the future. I believe this is a really exciting thing to work on, um, and this is really something which you, as a high school student, can can have a future on in the science of chemistry and physics and a little bit of biology too. So that was all from my side. Thanks a lot for your